Today we will learn the importance of organosilicon compounds in organic synthesis. As we know, silicon belongs to the carbon family, but in the following aspect it is different from carbon. That is, it has larger size, it has atomic radius of 117 picometer, whereas carbon has 77 picometer. If you compare the electronegativity, this silicon is less electronegative and it is more electropositive because it has electronegativity of 1.64, whereas carbon has electronegativity of 2.55. Silicon has greater affinity for electronegative atoms like fluorine, chlorine and oxygen. Monomeric silicons are known as silanes. A silane that contain at least one carbon silicon bond is known as organosilanes, and these are the important compounds in the organic synthesis. That is, organosilanes means that contains at least one carbon silicon bond, and silicon carbon bond is covalent in nature, and silicon acts as electrode. Means silicon, due to its low electronegativity, it is going to act as electrophile, and nucleophiles will directly attack this silicon atom. So this is basic introduction regarding organosilanes. So if you come for the synthesis of organosilane, there are three methods we can prepare organosilanes. The first method is direct synthesis by Rochow-Muller process. Here the alkyl halides, upon reaction with silicon powder in presence of copper as a catalyst at 300 degrees centigrade, it is going to form corresponding organosilanes. So this is a direct synthesis, that is by using silicon powder and alkyl halide in presence of copper as a catalyst at higher temperature. The second method is metathesis. Here the silicon chlorides on reaction with organolithium reagent is going to form organosilanes, that is metathesis. And the third method is important method, that is hydrosilylation, or also it is known as hydrosilation. Is the one of the most useful catalytic reaction where addition of silicon hydrogen to unsaturated bond leads to the formation of organosilanes and organosilicons. So this is very important synthetic route for the preparation of organosilanes. Here the silicon hydrogen will add to unsaturated bonds like alkene, alkyne, carbonyl, imine and nitrile in presence of catalyst. Here the catalyst may be platinum. Platinum is the widely used catalyst. So it is going to form anti-Markovnikov product. Means silicon is going to add to the less substituted carbon. Means if it comes in the case of alkenes, it is going to form anti-Markovnikov product. So this is hydrosilylation reaction. Also it is known as hydrosilylation reaction. Means silicon hydrogen bond will add to the unsaturated double bonds. So it is going to form corresponding organosilanes or organosilicon compounds. And these are the three methods or three ways for the synthesis of organosilanes. And if we come for the reactions, so first important reaction is protecting reaction. So variation of R group on the silicon can provide an unlimited range of protecting groups for oxygen, nitrogen and carbon. So here in this protection reaction, we are going to protect a reactive functional group, so thereby making it less reactive. In such case, this silicons, organosilicons, plays a very important role. That is, it is going to protect oxygen, nitrogen and carbon by just variation of the three alkyl group attached. So here the general reaction of protection of alcohol is given. So alcohols, upon treatment with trialkyl silyl chloride in presence of base, it is going to protect the alcohol. So thereby it is making the alcohol less reactive, and if you want to remove this protecting group, so it is just by adding tetrabutyl ammonium fluoride salt is just enough for the deprotection reaction. So this is one important reaction of protection of alcohol group, and at the same time we can protect terminal alkane. So terminal alkane, upon treatment with butyl lithium, if we add trialkyl silyl chloride, it is going to protect terminal alkanes. So if we want to protect this terminal alkane, we don't want to react this one, so we need to make this less reactive. In such cases, it is protected by using silicon. Similarly, amines also can be protected by using trialkyl silyl chloride, and deprotection is just by tetrabutyl ammonium fluorides or water molecule are just enough for carrying out deprotection reaction. So this is regarding protection reaction. And if we see the commonly used protecting reagents are tertiary butyl dimethyl silyl chloride, is abbreviated as TBD, M.Sc, triisopropyl silyl chloride, TIPS-Cl, TIPS chloride, tertiary butyl diphenyl silyl chloride, TBD, PS-Cl, and texyl dimethyl silyl chloride, TDS-Cl, and simplest organosilicon, which is going to act as protecting group, is trimethyl silyl chloride. So that is the simplest, and these are the most commonly used protecting groups for various functional groups like OH, NH, or terminal alkynes. So if we come for the other reaction, so aryl silanes will undergo ipso substitution reaction. Means the substituent, virginal substituent which is present, will be replaced by an electrophile. So that is known as ipso substituents. Means this is the virginal substituent, that is trialkyl silane, which is attached directly to the aryl ring. This will be get substituted by a electrophile. So such kind of electrophilic aromatic substitution reaction is known as ipso substitution reaction. So why it is undergoing ipso substitution reaction is because the silicon is going to stabilize the positive charge at beta position through hyperconjugation. So whatever the bonded pair of electrons present here, it will be donated to this empty p orbital. So thereby it is going to form a double bond here, and silicon is going to carry positive charge. Because silicon is having empty d orbital, so it can resonate. Hence thereby it is going to stabilize the beta carbon. So hence aryl silanes will undergo ipso substitution reaction. So this is very important. If you have aryl silane, then you can expect ipso electrophilic aromatic substitution reaction. So this is very important reaction of aryl silane. Even in presence of alkene also the same thing will happen. Means the beta position will be stabilized by hyperconjugation. So next reaction is addition reaction. So if we take vinyl silane, they undergo addition reaction with electrophile with retention of configuration. Means here if we take vinyl silane, so here the two groups are on the same side, so it is Z vinyl silane. So if it is treated with electrophile, then it is going to form the addition product with retention of configuration. Means electrophile will add to the position where that silicon is, where that silane is present. So it is going to undergo with retention of configuration. If we take Z vinyl silane, it is going to get the same product without any inversion of configuration. So if we take E vinyl silane, it is going to form E product. So that is, there is retention of configuration. But in some cases, like if we take bromine, there are chances of getting a mixture. So next is Peterson olefination. This is a very important reaction of organosilane. silenes. That is, the preparation of alkenes from alpha-silyl carbanions and carbonyl compounds, and is known as Peterson olefination. So, we are going to get alpha-silyl carbanion. So, this is the reaction how we can generate alpha-silyl carbanion. Means I am going to take this silane chlorosilane compound. Upon treatment with magnesium, it is going to form Grignard reagent. So this is an synthetic equivalent to carbanion. So this carbanion equivalent, if upon reaction with carbonyl compound, in presence of acid or base, it is going to form alkene. So that reaction is known as Peterson olefination reaction. So that Peterson olefination reaction is just a preparation of alkene from alpha-silyl carbanions and carbonyl compounds. So it is going to generate alkenes. So this is the reaction for how to get alpha-silyl carbanion. So this alpha-silyl carbanion reacts with carbonyl to form an intermediate. That intermediate, upon treatment with acid or base, it is going to form alkene. So which type of intermediate it is going to form is, we will see in this one. So addition of alpha-silyl carbanion to carbonyl compound gave rise to mixture of diastereomeric silyl carbenols, which can be isolated and separated. So whatever the alpha-silyl carbanion, if it adds to the carbonyl compound, it is going to form diastereomeric silyl carbenols. So these two are the diastereomeric product. Means you can see here the silyl group is below the plane and this OH group is above the plane, and in this diastereomer both are below the plane. So it is going to give mixture of product because it is going to generate a stereo center. So this is one stereo center and this is one stereo center. So obviously if we have two stereo center, means if you can use the formula, that is 2 power n. So it is going to form 4 isomers. That is, from this diastereomer you have 2 isomers and from this diastereomers you have 2. Means silyl and OH group, in this case it is below, or other possibility is both can be above. And here also OH is above and silyl group is below. Other possibility is silyl group may be above and OH group may be below. So here I have mentioned only one of the 2 isomers because these two are the important. So it is going to form diastereomeric silyl carbenols. So this diastereomeric silyl carbenols, upon treatment with acid and base, they are going to yield alkenes. So what happens if we treat these diastereomers? Before reaction we need to isolate and we need to separate this one because it is a mixture. So we need to subject this diastereomers for chromatographic separation so that we can get pure diastereomers. So pure diastereomers, upon treatment with acid and base, it is going to form alkene. So first case we will see what happens if we treat a pure diastereomer with acid. So pure diastereomers, upon treatment with dilute acids like acetic acid, H2SO4 or even Lewis acid, results in stereospecific anti-elimination to give alkene. So here the term you need to remember is stereospecific. Means if I take one of the diastereomer where silyl group and OH group are anti to each other, if I treat with acid, dilute acid like acetic acid or H2SO4, or even I can treat with Lewis acid, it is going to result in the formation of stereospecific anti-elimination to give alkene. So here the acid is going to protonate this OH group, so it is going to form OH2 plus. So it is a very good leaving group. Now this silyl group and this OH group, there will be anti-periplanar transition state is possible, and through this anti-periplanar transition state, the silyl group and OH2 group are get eliminated to form E-alkene. So here it is stereospecific, means the starting material is anti, so the starting material configuration is retained. So that's why it is called stereospecific. Anti-product will give E-alkene. So that through anti-periplanar transition state. Suppose if I take syn diastereomer. We got two different diastereomers. I treated this diastereomer, I got E-alkene. So what happens if I take the other diastereomer? In the other diastereomer, the silyl group and OH group are on the same side, means they are syn to each other. If I treat this syn diastereomer with acid, so it is also going through anti-periplanar transition state, and it is going to give Z-alkene. Means syn is the starting material, so we need to end up with Z-alkene because it is a stereospecific reaction. Okay, so this thing is very important. If you use acid for elimination, then you need to see the geometry of the diastereomer. If it is anti, definitely you are going to get E-alkene. If it is syn, you are going to get Z-alkene. That is in the case of acid treatment. So what happens if you treat with base? So if you take pure diastereomers, you treat the pure diastereomers with base like NaHKH or tertiary butoxide, potassium tertiary butoxide, results in stereospecific syn elimination to give alkene. In the case of acid, it has undergone stereospecific anti-elimination, whereas if you treat the pure diastereomers with base, it is going to result in stereospecific syn elimination to give alkene. So if I take this diastereomer where OH group and silyl group are anti to each other, if I treat with base, first it is going to deprotonate. It is going to form an anion. So this anion, what it is going to do is, it is not undergoing through anti-periplanar transition state. It will undergo rotation. So rotation of bond occurs to make silyl group and oxyanion syn. So why it has to undergo rotation is because silicon has affinity for oxygen. Already I mentioned silicon has greater affinity for electronegative atoms. So here this O minus will react, or it is going to combine with this silane. So it is going to form syn periplanar transition state. Because of this interaction, so if you take anti, it will be get converted into syn. Then this will undergo syn elimination to give Z-alkene. So that is the case of anti. Anti, if you take OH and silicon, if they are an antiposition, if you treat with base, first it is undergoing deprotonation. After deprotonation, since silicon is having affinity for oxygen, so it is going to coordinate with the oxygen. So for coordination, it has to rotate. So then it is going to rotate and it is going to form a syn periplanar transition state. So this syn periplanar transition state will undergo stereospecific syn elimination reaction to give Z-alkene. So what happens in the case of OH group and silyl group are on the same side? Then there is no question of rotation. If you treat with base, deprotonation will take place and it is going to follow syn periplanar transition state. So there will be syn elimination takes place to give Z-alkene. So here the diastereomers upon treatment with base, whether it is anti or syn, you are going to end up with Z-alkene only. So this is very important thing, you need to keep it in mind regarding Peterson olefination reaction. So once again I will repeat, Peterson olefination reaction is an reaction where you are going to prepare alkenes from alpha silyl carbon ions and carbonyl compounds. So alpha silyl carbon ion, upon treatment with carbonyl compound in presence of acid or base, you are going to get alkene. So this alpha silyl carbon ion is going to react with carbonyl. It is going to form diastereomers. So this diastereomer is nothing but beta silyl carbonyls. So these diastereomers upon separation on treatment with acid, the OH group and silyl group, if they are anti to each other, when it is treated with acid, it is going to form E-alkene. If they are syn, it is going to form Z-alkene. So it is stereospecific anti-elimination. So if the diastereomer is treated with base, then it is going to form in the both diastereomers are going to form in periplanar transition state, and it is going to form Z alkene. So if you look at the example, so here OH and silyl trimethylsilyl are anti to each other. If I treat with acid, there will be anti-periplanar transition state. So depending upon this group orientation, you are going to get E alkene, because here it is anti, so you are going to get E alkene. So the same example with different diastereomers. Here the silyl and OH group are syn to each other. If I treat with acid, there will be anti-periplanar transition state, and the product alkene is Z alkene, because the static metal stereochemistry is syn, so I will end up with Z alkene. The same diastereomers upon treatment with base. So if I treat the diastereomer where OH and silyl group are anti to each other, then oxyanion will form. That oxyanion will undergo rotation, because silicon is having affinity for oxygen, so it is going to form syn periplanar transition state, and upon syn elimination, stereospecific syn elimination, it is going to form Z alkene. So if I take the diastereomer where OH group and silyl group are syn to each other, then if I treat with base, it is going to form oxyanion, and it is going to form syn periplanar transition state, and it will undergo stereospecific syn elimination to give Z alkene. So if I summarize Peterson olefination reaction. So anti-elimination will takes place in presence of acid as catalyst. So if you are using acid as catalyst, you need to check for the static material stereochemistry or static material geometry. If the groups are anti, then you are going to get E alkene. If the silyl and OH group they are syn to each other, then we are going to get Z alkene, and in presence of acid, it is undergoing through anti-periplanar transition state. So if you come for syn elimination, both anti and syn diastereomers, they are going to form syn periplanar transition state, and they will show syn elimination to give Z alkene. So this is the summary regarding Peterson olefination. So you need to remember this anti-elimination and syn elimination. So, and also the static material geometry, whether they are opposite or same. So the case if they are anti, E alkene will be formed in acid catalyst. If they are syn to each other, or if they are same side, then acid catalyst will give Z alkene. But if you treat with base, irrespective of this one, it is going to form Z alkene. Why it is going to form Z alkene is because silicon is having affinity for oxygen. So this is regarding the summary of Peterson olefination. So with this, we have seen the important properties of organosilicon compounds, how it is prepared, and what are the important reactions. So organosilicons, their important reactions are protection reactions, ipso substitution, and Peterson olefination reaction. Thank you.